Hi guys, welcome to Learn Electronics Repair and a parcel here. So this is from a guy on one of the other islands, Lanzarote, okay? So this came kind of roundabout way from, do you remember that thing I fixed the burnt PCB for the paper folding machine, yeah? So via a friend of his, basically, this guy's in a band and this is their amplifier. And it's broke. It's broke. He said it blew up or went bang, and I think it did this actually during a gig. Yeah. So I do know what it is. It's a QSC amplifier. I had a quick look. There are schematics for this, and I could see that this used bipolar transistor output stage. So I've ordered some of the output transistors. They're a common pair anyway, MP, MP, MP. I need them for other repairs, but I ordered 10 more of each, knowing this thing was coming in, yeah. So they're already on the way, could be here fairly shortly. Let's have a look to see why this blew up, yeah, what went bang. How spectacular is it? I know it might seem so of late, but you know, this is not an audio repair workshop. You know, guys, I'm a general electronics repair workshop. It just seems at the moment I have a lot of amplifiers coming in for repair. That may be related to the fact that there's lots of venues here, so they have amplifiers. It may be related to the fact that for whatever reason they seem to blow up on a regular basis here. Or it may also be related to the fact that this sort of musical equipment, professional music equipment, basically, is one of those things that are actually worth repairing, yeah? So while I take the bubble wrap off this, you guys chat down there, and then let's see what we have. And there we have, so QSC audio, Pro 3000 watt, upside down, PLX3002. I'm pretty sure I've seen similar, if not the same as this one before. Because we know it went bang, the first thing we'll do is open this up and have a look inside. And the first thing I'll just note, by the way, and I probably haven't seen this before because I would have remembered this. So this one, the actual cover which comes off is on the bottom. So maybe the amplifier boards are upside down in here. Some mode switches here. I've seen this sort of thing before. I do feel like I've seen something similar to this previously. Okay. Let's have a look then. So in fact it is upside down, we could say. I've not seen exactly the same as this, but first impressions. Switch mode power supply, okay, mains filters, looks like a standby supply, so that is a standby supply. This is the main supply. I'm guessing, sort of guessing, I can see the bridge rectifier down here, I can see a couple of big devices down here. This looks like a PFC inductor to me, so I'd say this is PFC. Although the devices are over there, I think this is actually the switching devices for the transformer, just a bit of a strange layout, you could say. Yeah, with NTC with the relay that shorts it out when it's powered up, basically. So this is your inrush current limit. Large capacitors, lots of other capacitors. And then this must be the amplifier. I can see there's a fan at the front of this. So under here is the amplifiers, and we need to get this off. Okay, so this kind of just lifts out. This is the fan at the back of it. Danger 400 volts, high energy. Hey, I like this. High energy 400 volts, use safety glasses when servicing. Interesting. I'm not seeing that particular warning before. Don't poke your fingers in, there's probably a better one, but there you go. I suspect because of that, I'm going to find that these heat sinks here are not at ground potential. I wouldn't be surprised if they were like plus HT and minus HT. Would not be surprised at all. I mean, they're not bolted down to the chassis, they fitted to the PCB, so that's another very good indication that we're going to have some very high voltages on here. Okay, and now we can see the heat sinks, which I was just mentioning. I can see down here the pins from the power transistors. Okay, and yeah, the rest of them are kind of like under that lot. So to get to those, it looks like I'm going to have to take the heat sinks off, and to get the heat sinks off, it looks like I'm going to have to get the PCB out. Okay. So where's the problem? Well, realistically, it's going to be in one of three places, I would say. Either A, the PFC is blown up. B, the switching transistors and power supply have blown up. Or C, there's a short in the output. That seems the most likely scenario. Okay, are there any fuses? Well, I don't see any fuses, but what I have just realised is that these here are diodes. Okay, so there's 4 of them, but they're probably the diodes on the output of the transformer here, the switch mode, which really does look like a switch mode to me. These down here are actually transistors. Now, if it was PFC, you'd expect to find a MOSFET and a diode. I don't see that, so maybe this doesn't have PFC. And another good reason for that, these are 200 volt capacitors. Makes me think that these are actually the bulk smoothing capacitors, not output capacitors. These are the output capacitors. So I can make a few checks. We can check for shorts on the output of the bridge rectifier, but if there is PFC, which I don't quite see at the moment, even if there was a short further in, we probably wouldn't see it because of the PFC diode. We can check on these transistors here, which I'm pretty sure we do derive that for shorts. Other than that, I think we're going to have to take this PCB out. So let's make these checks first. Okay, so ohms range. Let's measure across the bridge rectifier. It's almost certainly the 2 outer pins, and this one space further away is almost certainly the positive. So I don't see any short there. Always check, of course, the meter is working. Yes, it is. So I don't see any short across those. Okay. Across the input on the AC, let's just have a look. Hundreds of kilo ohms. These output, or rather probably power supply driver transistors, I would say. Don't see any problem in regard to shorts across the collector emitter, so they read okay. How about these diodes? I'll try this in diode mode. Reads like a Schottky diode or fast rectifier type thing. That reads the same. This meter will bleep. I can change the threshold, by the way, but don't worry about it. It's not bleeping because it's a short. I have another multimeter coming, by the way, which has the Mr. Bleep facility. So they read, as far as I can tell, okay. I can only get to 1 amplifier, but we can have a look. So, well, we're in diode mode. These are strange transistors. I'm not sure what they are. Maybe not what I thought they are, or it's not marked right because this says base collector emitter. You would honestly expect... Oh, no, they're not strange. You know what? Is they mounted upside down, that's why. So this is why this is the base. Let's go collector emitter. What do we have? No short. Yeah, base emitter is going to read low because of the base emitter resistor. Base collector reads like a diode, so they're okay. How about these ones? Don't see any shorts there either, but bear in mind I can only get to one of these. So going on what the customer told me, I'm going to get this PCB out and let's have a good look. Well, this says replace the fuse as marked. So there is a fuse somewhere. Ah, it's there. Yeah, tucked away. Okay, let's try that. Fuse reads okay. So whatever went bang did not blow the fuse. Right. Schematic then. So QSC PLX3002. This is electro Tanya. You know, I use this quite a lot this side. Very good for schematics. I've never had a problem with anything I've tried to download from here. You won't just find, well, obviously there's adverts, but you know, you won't find like links which download other stuff. Let's just confirm what I can see then. So amplifier input, okay, LED signals. This is your output stages. So positive section, negative section. This is for one channel. That's why I see 4 heat sinks. I saw 4 transistors on the one I looked at, but I was probably only looking at the one side, positive or negative. I need to get the board out to get to the other ones. Step driver. So this is a class G amplifier. The step driver will effectively change the voltage rail here. Okay, higher or lower voltage depending on the audio level. In fact, we can probably see that actually. Doesn't exactly tell you what the step voltage would be, but it's going to be probably switching between 50 volts roughly and 100 volts roughly. Okay, and that's done with this MOSFET here. So any problem in this part of the circuit, especially a shorted MOSFET, will probably cause it to blow up. It may be, yeah, look here, plus mid rail and plus high rail. So mid rail is probably 45-50 volts, high rail is probably 90-100 volts. This diode is there to stop when this MOSFET turns on the higher voltage going back into the mid voltage supply. Okay, it's possible the reason the fuse isn't blown is a 15 amp fuse and maybe the fuse in the plug blew first. That's a possibility if it really did go bang, which he says it did. Okay, so we have a class G amplifier and we have, yeah, bridge rectifier, 3 look 200 volt capacitors. I can see 6 on here, so 3 and 3. That's the big blue ones we could see. Transformer, let's see, yeah, this looks like it's a LLC, half bridge resonance circuit. That's your transformer primary there. This is your inductor, so L and C is the capacitor, I would say. So basically these transistors are the ones I was trying to measure. Yeah, collector emitter, they looked okay. So this is the power supply. These switch on alternately, one after the other, and it basically switches this end of the transformer to high voltage, low voltage. So this is probably 320 volts, 0, 320, 0. Other end of the transformer primary goes to the junction between the groups of 3 capacitors, yeah, which is effectively 160 volts. So that's how it drives. That's like an ATX, very much like an ATX. Okay, driver IC, IO, yeah, this is like a MOSFET driver which is being used. Oh, they're not transistors, Luke. They are IGBTs. Can you see that? Yeah, these are IGBTs. More like a MOSFET than a transistor. Okay. That one will be the pulse width modulator for the power supply. Okay. And then we can see all the secondaries and the various diodes. I was testing some of these diodes. And from a quick glance, I didn't really see any problem here. So the question is then, can we check these voltage rails for shorts without removing the PCB? And the answer is not easily, because we have the emitter resistors, which are going to be low value resistors, yeah, 0.47 ohm each. These could have blown open circuit. That quite often happens when amplifiers blow up, and I can't even see where they are, apart from saying they're probably under here somewhere. So yeah, PCB is going to have to come out. And for once, this is relatively easy to a point. So screw there, another screw there, take those out, and then it moves sideways and it lifts off. Yeah, that's how it comes off. This lot is soldered to the board, but I think I can probably get this whole thing off the back here. Yeah, that comes off. These, I'm not sure if I can actually unplug them. You don't seem to want to move easily. You would think so, but don't want to damage that. But again, just a cable tie there. This whole board will come off, and it looks like that one will do the same, which actually probably makes this easier to test on the bench. So let's unbolt these as well. Well, it's probably a good thing I decided to take this PCB out, because underneath it, in the general area of where the power comes in, I found that. I found that. I wonder if that's related to the problem. Well, it doesn't look particularly fried. I'd say it's particularly dead. And now we can see underneath the PCB. I mean, I think this is just dust. Maybe a bit of discoloration. Okay. So these are the mounts for the heat sinks. Again, insulated from the case, which tells me they are at high potential. In fact, if we can easily remove one, let's just do that and have a look. I can see now all the pins from the 4 transistors on each one, at least. I'm interested to see if this is where the emitter resistors also are. Well, it came off easily, or almost easily. Something holding this in place. Something here holding this on. I think it's just stuck to these 2 components. Okay. I don't see any screws in there, at least. Yeah, it's just stuck to it. Okay, off. So I'd say these are the emitter resistors. Don't look very high wattage though, but yeah, it looks like probably yellow, violet, silver, which would be 0.47, and we can see all the devices, and we can see some other devices under here as well. Okay, this one at the end, I'd say almost certainly is going to be the MOSFET, which switches the voltage rails, and the diode that we can see that prevents the voltage going back down from the high voltage into the medium voltage. So while here, I've just removed the rest of the heat sinks. We can just check these now. So 0.41 base collector, base emitter, expect it to be low because of the resistor. Okay, I'll show you that in a minute. Looks okay. Okay, I think these are the ones we actually managed to test before we took the heatsink off. Okay, and then collector emitter. I'm not sure if these are the NPN or PNP. Well, actually, I know these are. Yeah, these are the NPN. So we'll put the positive on the collector, black on the emitter. You'd expect that to read open. It's going quite high. Reads the same. Okay. Let's go on these. Are these also NPN or PMP? Well, these look like they're the PMP. Yeah. Again, the low resistance. And then with the black to the collector, it's the same sort of value as the other ones. Okay. Are these NPN or PMP, these ones? Looks like these are the other PMP. So black to the collector. I mean, these are all in parallel, so you'd expect them to read the same. And then these must be the other NPN ones. So they're reading about the same as the others. Okay, the resistor we can see from the base to emitter is probably 4.7 ohm. That reads 15. Reads about 2. Interesting. I'd expect these to all read the same. Of course, now they do. Must have been some capacitor somewhere to charge up on these ones. Yeah, 15 ohms. So that's why we see a low reading in diode mode when we're measuring from the base to emitter, okay? Yeah, obviously a capacitor has to charge somewhere. So they look all right. These are the MOSFETs and the diodes for the voltage switching. Reads like a diode. Ah, that one reads short. No, it doesn't. Interesting. Thing with capacitors, I think. Okay, all read like diodes. And then the MOSFETs, well, gate. Doesn't really tell us very much, but we should be able to see the parasitic diode here. There. In that direction, okay. Notice it only just starts to bleep at 0.5, yeah. Reads okay. Reads okay. So I don't see any problem there. Maybe it was a cockroach that went bang. Although you would expect it to show a few more signs of that. Yeah. The emitter resistors are in pairs, so obviously that would double the wattage. They're in parallel by the looks of it. Yeah, 0.4. There's going to be one per transistor, so they're obviously just in pairs to increase the wattage and decrease the resistance. So they're at 0.2 in total. So the fact that these also read okay suggests that there's nothing happened where a lot of current has flown down this way. Really, I only need to read one of these. If I show you, they're actually in parallel loops. So this end to this end, and this end to this end. So if we just measure one of the pair, it's enough. 0.39. Same basically. And while we're here, we may as well just have a quick look at the driver transistors as well. Probably one NPN and one PNP. Again, there'll be a low value resistor there. Base emitter. Well, you would think so. Look at that one again. Well, does that read the same as this one? No, it doesn't. That's the PNP channel. This, I think, is the NPN. That reads low. Interesting. Let's try again. So this PNP probably. Of course, the schematic would tell us. Looks like a transistor. Other one, I think, NPN. That reads low. Okay. Base emitter. That one. This pair. Reads like a transistor. NPN. And the other one. Also has that low reading. So that one and that one. And that looks like the same as this one. This one. Does this have the low reading as well? Yeah, we've seen that on all of those ones with like the metal heatsink here on the plastic type, okay? If you see a reading like that and you're not sure if it means it's good or not, go to the resistance range and see what you see. If you see what looks like a standard resistor value, you know, it's probably okay. So 220 ohms. So I don't find any obvious problem with this really. We had a look around the power supply area before, at least from the top side. I can see the switching transistors. I think the next thing then would be to power this up and let's just see what it actually does. Maybe it was an exploding cockroach, but then you think it would have been a bit more, well, exploded, yeah. Okay guys, different day, but we're continuing with this, so we're going to try and power this up. We should be able to power this up on the bench. I've connected the switch. I've actually just connected the power onto here, so that goes straight into the input. So we still have the fuse. We can use the current limiting light bulb. I have the heat sinks removed, okay, so these are off, but that shouldn't stop us powering this up. We're not going to actually run any audio through it at first. I just want to see what happens when it powers up, if all the voltage rails come up. If they do, I'll put the heat sinks back on and we can give this a go. Again, I should be able to run this on the bench with or without the heat sinks on. These transistors, N-type and P-type, if we just look at the schematic for a moment, you'll see this type of design has the power rail. So this is the rail which switches between, well, I think it's actually 55 and 110 or something on this one. It does tell us in the schematic, but somewhere in that region. We can just look at the power supply section and we see we have a plus 67, plus 117, and then minus 67, minus 117. So these are the 2 positive and 2 negative rails which are switched by these MOSFETs. Okay, so the negative supplies actually come to the emitter here on the NPN transistors. The positive supplies come to the emitters on these PNP transistors, and you'll see that all the collectors here are connected to all the collectors there. So it is just conceivable but unlikely that the connection between all the transistors is actually done by the heatsink itself, although the fact they have heatsink compound on, I'd say that is just not the case. But we can just be absolutely sure. So if we go onto the transistors, you can see they're connected. Goes to there. That's a plastic one. Yeah, all here. And those all connect to here. So these are NPN and PNP. Like the schematic says, all the collectors connected together. Obviously it doesn't connect to the other channel, but the other channel, again, all connected. Okay, I'm sure you can hear that bleeping. I hope so. So let's just power this up. We'll put the limiter on, as I said, and let's see what it does. Okay, so we can have a look, I think, even with the current limiter on, to see if any output's coming from the power supply. You'd expect to have some voltage there, so I need to find ground. I'd say the best place to find ground is on the speaker output. In fact, you can see there. Goes to power ground. Okay. That goes to, well, the center tap on the secondary there. That'll be ground, little triangle symbol, which matches the one we see here. Okay. So if I measure from speaker out, black wires here, to the emitters on these transistors and power it up, I should see some voltage. So what we should see on the emitter would be the plus and minus supply rails. Okay, so we go to volts. We'll just power this up and we'll have a look. So do we have any power supply? Basically no, but the light bulb is getting fairly dim. That suggests there's no actual supply coming out of this thing. Right. Another good way to test if the power supply is running is just to put your scope probe near the transformer. You don't need to connect anything to it, just literally put the probe near there and you should be able to see if it's actually oscillating. So let's try this. And I would say it is not oscillating. You'd expect to see something there, just picking up the radiation, if you like. I'll just go to a more sensitive setting. Try again. Well, that was that low frequency ripple. Well, maybe something there. Let's have another look. No, just low frequency ripple. So that is not running either. Okay. So the first thing we should check is whether the standby supply is running or not. Because if the standby isn't running, and that's what we can see here, the main supply isn't going to run. Okay. This is definitely 100% a standby supply because this chip TOP top 210 PFI, I recognise that type of number TOP This is going to be like an all-in-one switch mode controller with a built-in MOSFET. We can find a data sheet for this, I would think, quite easily. So TOP210. Yeah, very simple switch mode controller. There we see it. So there's in actual fact only 3 connections to this: control, drain and source. The other ones are no contact or no connection. Drain, source, control, that is literally it. So let's try the same trick with the scope probe and see if we can detect whether the standby is running. Okay, so once again we just put the probe near to the transformer. We switch it on. And I would say there's no standby there. That's much too low a frequency waveform for the switch mode. Okay, so standby isn't running. Okay, so that's the first thing we need to sort out. So looking at the schematic, that's the top 210, that's the chip. Okay, this is the transformer primary, that's the secondary, this is your standby voltage here. So it says it's 16 volts, there's a 10 volt Zener here. So there must be about 6 volts on the other end of the Zener. You would assume for there to be 16 volts on that end. It says it's a 10 volt Zener. Okay. It's a SOT23, so it looks like a transistor, but it's a Zener. We can see Q99 here, and the emitter of Q99 is also the 16 volt supply, which goes to cathode of D66 as well. So we should be able to find that point quite easily. And there is Q99, so this will be the emitter. Yeah, and it goes to D65. So that's as good a place as any to find the standby. Let's have a look. Now here is the interesting thing. So you can see the output 16 volts smoothing capacitor C139, but look, the other end of that does not go to ground, safety ground, goes to pry low. And we can see the same here on the controller chip, goes to pry low. So this circuit always, look, even including the secondary, is referenced to pry low. And pry low is here, the negative end of the bridge rectifier. This is the mains coming in. So pry low is hot ground. We would call this hot ground. They call it pry low. Okay. You see it here as well. So this circuit, even the output of it, although they use a transformer to do the step down of voltage, is not isolated from mains. This is still connected to primary low, hot ground. Okay. So to measure the voltage on here, 16 volts, we need to measure it with reference to there. Okay. So we need to find that. So that's where the bridge rectifier is. And that's actually here. So I'm guessing that is the negative end, or primary low, or hot ground. That is the positive end. Can we see that? Not with that big clip on there, we can't. And it's not even easily marked without the big clip on, but I think we can say the chamfered edge here is the positive. We can soon test with the multimeter anyway, or we could just figure out what goes to the negative end of these capacitors. Yeah, probably this end. Well, let's use the multimeter, diode mode. So if these are the AC terminals, 2 of them, to the one with the chamfered end, here we see a diode. We see a diode, and then if this is the negative out, which is the hot ground, of course. Yeah. Diode junction. So that is hot ground. So that's our reference point for the 15 volts. 16 volts. So to make life a bit easier, I've just tagged a wire onto there. We can use this now to clip our scope, as long as we have a scope which is not grounded, an isolated scope, or we can clip the multimeter negative lead onto there. We can take some voltage measurements around here now and see if we can figure out why the standby supply doesn't appear to be working. So first thing, do we actually have standby? It looks like we don't from what I can see, but let's just double check. No, we have no standby. Okay. So because the light bulb is coming on with some amount of brightness, it seems to be drawing about 20 watts. I'm only guessing. I mean, I could actually measure that with the clamp meter actually and see how much power this is drawing. In fact, why not? About 150 milliamps. Okay. Obviously the light bulb's also dissipating some wattage as well because it's staying on with some brightness. But we'll have to assume the current through the light bulb is the same as the current through here. So at 220 volts, 150 milliamps, well, we can roughly work it out. So 100 milliamps would be about 22 watts. Yeah, because 1 amp would be like 220 watts. So 150 would be about 30, yeah, 33 watts. That means something is drawing some power here even when it's not running. So let's get the thermal camera and see if we can see anything down here getting hot. Okay, so there's the chip. We can see that. Let's power this up. No, nothing there. Let's take the macro lens off and let's have a bit of a look around. No, nothing particularly that I see. Quick look. Okay. Nothing noticeably getting hot. We can see the multimeter, DC volts. This is still measuring the current. What do we have? Definitely no standby. Now, there is a possibility, I just want to check for here, because the light bulb is limiting the current, that's also going to reduce the AC voltage coming in here. It's conceivable that there's not enough voltage to start the standby supply, although that should probably start with about 80 volts, I would think. So we can just check what voltage is actually coming in on here. And we can also try the higher wattage current limiter for that matter. Power's off. Do we have a connection? Yeah, it's reading some resistance, so I obviously do have a connection. So voltage AC. Power on again. What do we actually have? Yeah, there's over 100 volts there, so that should be more than enough to start that standby supply going. So it's not a case that we've got like a red herring, I would say. We do apparently seem to have a problem with the standby there. In fact, there's a test circuit here. Look, and this shows 40 volts supply as being sufficient to start this thing running. Okay, so let's have a look on the chip, or maybe some components connected to here which are a bit easier to probe. So pin 5, this is the drain. This should have high voltage on. Okay, and that's pin 5 down there. We can actually get down there quite easily. The power's off, but again, if you want to make sure you actually have a good connection, just go to resistance range. We can see some resistance. So yeah, we have a good connection there. So let's power this up and see what we have. And we have no voltage there. Okay. Nothing on pin 5. So we can see here, primary low. This is the hot ground, goes to pins 1, 2, 3, 7 and 8, all connected there, and then pin 5 goes to the transformer, and the other end of the transformer goes to primary high, which is HT. Yeah, so this is primary high. This is the positive end of the large smoothing capacitors. These ones here, this is positive, this is the junction, that's negative. Okay, so this is primary high, junction, this is primary low. Okay, hot ground, and we can just check that. So from primary high here, we're on resistance range to the transformer. Yeah, reads okay. Other side of the transformer primary is here because this goes to the chip. Pin 5. Yeah, this is 1, 2, 3, all connected together. 4, yeah, 5, 6, 7, and 8. So that's how it should be. Shows you on the schematic, all connected together. So the transformer primary is open circuit. This point here, well, this will go to hot ground, as I said. Yeah, okay. So the reason our power supply isn't working is because the transformer is open circuit on the primary. Quite possibly this chip is faulty. Is there a short here? $140 ohms. It's quite low, so I would say that the chip has failed and taken the transformer with it, and that's probably what went bang. I'm not sure if we'll visibly see anything if we unsolder the transformer, but it doesn't quite get us out of the pickle we are in, but I think I can probably get us out of it. So let's unsolder this transformer anyway. So there's a good reason why this isn't working. It looks like the track's broken there, but it isn't. You can see if I just angle it. So this is from the pin 5 of the chip to the primary, and this one is to the high voltage in. And you can see, we can just check it again. So here to here is good, and then here to here is good. So yeah, open circuit coil on the transformer. Now the question is, can we get one? I'm guessing probably not. But if we can't, I think we can probably fix this anyway. Let's have a quick look. Well, apparently I can from a UK seller. This is actually on eBay, but UK seller, Enigma Component Shop Limited, they have this. About $16. So that is a possibility. There may be other sellers of these. Okay, nothing on AliExpress, but I can certainly get these by the looks of it. So that's one option. If I do that, I will also get replacements of these ICs as well. I don't think I have them in stock. I can have a quick look. Yeah, I have a similar one, but not the one I want. But I'm sure I can easily enough get those. I think now we can actually see. So this is where the primary goes, and we can see it's like blackened down there by the looks of it. So it's probably when the thing blew. Interestingly, this should be the secondary by the looks of it, and seems to just go directly to that capacitor, though you'd expect. Well, in fact, there is a diode in the circuit, or several diodes. I see something else connecting here, but in fact the transformer doesn't have any connections to that pin. Yeah, you can see quite clearly there are no connections to the pin that goes into there. Yeah, so interesting as to why that is there, unless it's just using that as a effectively as a via. Okay, C143 is this capacitor. Yeah, looking at the circuit, that's the capacitor. There is a diode. There must be a diode in that there. While we're here, we should check to make sure there's no short on the output of this little supply, okay, regardless of what it's actually doing. So we have D62, that's the output diode, okay. We have C138, that's the output capacitor there, okay. Then we come through some diodes, and then we have the output here. So if we measure from hot ground, yeah, across this capacitor, we shouldn't see a short, and the same here across this capacitor, we shouldn't see a short. So we just need to measure basically across C138, C139. Well, there's C138, yeah, there's C139. So let's just measure across these, make sure there's no shorts. And here are the capacitors, C138, C139. Yes, charging up. Charging up. So there's no shorts on the output either. I would say then we need to either find a replacement for this transformer and change the IC. power it up with the current limiter, see what happens, see if we can get this part of the circuit working. It might be worthwhile, we can just check around the transistors around here just to see if we have any shorts, diodes, that sort of thing. I mean, that would be fairly easy to do. At least it would eliminate that. Or I could just order some of those parts. But if we have any shorts around here, they should be fairly easy to spot. I'm using this meter, by the way, because I'm not sure if my bench meter is properly isolated from ground because it's connected via the USB to my PC. I don't totally trust it when this thing was obviously on live voltages, yeah. As far as I know, it's isolated. I mean, I was connecting from the black meter terminal and measuring resistance from there to the USB ground. I couldn't see any connection, but hey, we can do it this way. So a quick look in this area just to be certain there's no other problems. Most of these are diodes, they're marked as diodes. Diode. Diode. This one was a Zener, I think. Diode, transistors, NPN and PNP. Let's go the other way. And we'll go back that way again. Yeah, looks like a transistor. This one. Oh, it's a diode. Yeah, it looks good. Looks like a Zener. In fact, it says Z9 on it. Probably a Zener. Another one here. These are not all in that part of the circuit, but they're all close. So let's have a quick look. V's like a transistor. Two more. Diode. Diode. Yeah, so all that looks all right. I would say that this is just literally blown. Well, we see that kind of like marker under there. Yeah, probably should clean that off actually. These diodes appear just to be there to drop the voltage a little bit. So this is generating 18 volts into this capacitor, and each one of these will drop 0.5, 0.6 of a volt. So that would bring this down to about 16.2, 16.5, something like that. So that's what those are doing from what I can see. There is a Zener in the circuit as well. So we know what's wrong with this circuit. We know why it's not working. We know why we have no output from here. But does this explain why the main power supply also isn't running? At first I thought this was a standby. I'm not totally sure that's exactly what it is. It seems to be an always running thing when the thing is powered up. Could be acting kind of like a soft start. It may have some internal, I haven't actually looked in the data sheet, but you know, it may just take a second or so to power up and power is on. Where's the on off switch? Oh, it's here. So that's before the bridge rectifier. So this isn't like an always on when the amplifier is powered up. This powers up after you switch the switch on. Again, it could be acting as a kind of a soft start. So this output voltage, we know it's referenced to hot ground. So whatever it supplies must be on the high voltage side of the circuit. That's before this big transformer. This is the isolated side, the safety ground side of the circuit, okay. And it probably powers the, yes, PWM. So this is your PWM and your driver for the IGBTs, and it powers these with the 16 volts. So if the 16 volt isn't there, the main supply can't start either. So I think for the moment that's as far as we need to go into the diagnosis. We'll just need to get our hands on the replacement part or find some other way to get the 16 volts running. And that would be to connect up a 18 volt. We find something probably 19 volt would do actually. Something like a laptop type supply. There's loads of room in this amplifier, so we could fit that in, connect it to power up from the mains, connect the output to replace this 18-volt supply. Because something like a laptop or switch mode is isolated from the mains anyway, it wouldn't matter that the ground of that is connected to hot ground, it wouldn't affect it. And we could literally fit another power supply to not use this one if we couldn't get the transformer coil. But as soon as we can get the transformer coil, I would much rather do that and repair it properly. Yeah. Okay, so last thoughts on that one, guys. Would you go down the proper route? Would you go down the other route? I guess it would all come down to what's available and what isn't available, but let me know down there. Okay, and I look forward to seeing you all soon again on Learn Electronics Repair. Ciao for now, guys.